Hello guys, this is the EdExcel AS Level Maths Paper 2 from the June 2019 series, and this paper will be having a look at the mechanics section. Now, I've already made the video of the statistics paper, so if you haven't already, please do check that out. Now, there's some important things to notice in this paper. That is, the first point is we take g to be 9.8 meters per second squared unless stated otherwise, and we have to give our answers either to 2 significant figures or to 3 significant figures. So with that being said, let's get straight into it. For question 1, at time t equals 0, a parachutist falls vertically from rest from a helicopter which is hovering at a height of 550 meters above horizontal ground. The parachutist, who is modelled as a particle, falls for 3 seconds before her parachute opens. Whilst she is falling and before her parachute opens, she is modelled as falling freely under gravity. The acceleration due to gravity is modelled as being 10 meters per second squared, and using this model, we have to find the speed of the parachutist at the instant her parachute opens. Essentially, over here in this question, what we have to do in this question, she starts off at a speed of 0 meters per second, and 3 seconds after she opens her parachute, and then she's accelerating at 10 meters per second squared. Now, if we go to our formula book, under the mechanics section, let's just highlight this. We'll be using the formula V equals U plus AT. And it makes sense that we use that because we've got seconds, meters per second squared, and if we multiply the units together, we get meters per second. So with that being said, for part A, using V equals U plus AT, we have V equals 0 plus A over here is 10, T over here is 3, so we have 30 meters per second. Now for part B, when her parachute is open, the parachutist continues to fall vertically. Immediately after her parachute opens, she decelerates at 12 meters per second for 2 seconds before reaching a constant speed, and she reaches the ground with this speed. The total time taken by the parachutist to fall 550 meters from the helicopter to the ground is t seconds. We have to sketch a speed time graph for the motion of the parachutist for t being t being greater or equal to 0, but less than or equal to capital T. Now, to do this question, if we begin by drawing a quick graph, so I'll just quickly do this. We have something looking like this, and we want over here our vertical axis. Okay, so I think that should be clear enough. Here we have V meters per second. Here we have T seconds. Now, he starts at rest, and then for 3 seconds, he reaches, after 3 seconds, he reaches a speed of 30 meters per second. Okay, so let's just actually add this in pen. We have over here 30 meters per second. Okay, and then, as we were told in the question, she then, after she opens the parachute, which is at this point, She then decelerates 12 meters per second for 2 seconds. So for 2 seconds, she decelerates. So that could take us to, suppose, to a point over here. Okay, and we can actually find out what this is. We'll find that later on. So here we've got 3 seconds, and 2 seconds later we end up at 5 seconds. And then we were told she reaches a constant speed, and this takes us to the end. So if she reaches a constant speed, we have over here this value being t, as shown over here. Okay, now with that being said, for part C we have to find to the nearest whole number the value of t. Now over here she's decelerating in this region over here at 12 meters per second. Now in a velocity time graph, the gradient of a line represents the acceleration, and therefore we can find out this time over here, this speed over here. We have the gradient, which we know is 12. We're finding out the change in y. We know the change in x to be 2. So what we mean by this, the change in y over the change in x is equal to 12. With that being said, the change in y, that's what we're finding. The change in x, that would be 2, and this is equal to 12. And therefore, the change in y is equal to 2 times by 12, which is 24. Now, this length over here represents 24, and therefore 30 take away 24 is 6. So we have 6 meters per second over here. And this satisfies the condition of decelerating at 12 meters per second. So, with that being said, we can split this shape into various other shapes for part C. We have over here a triangle, we have a trapezium, and then we have a rectangle. And we need to find the area of the triangle, the trapezium, and the rectangle, and equate that to 550. The reason being, the area under a speed time graph represents the total distance. So actually, let's just write that down. The area under the curve of a VT graph represents area. Okay, so with that being said, for part for part C, we have the total distance, which is equal to 550. So the total distance we know is 550 meters. Now we have the area of the triangle a half times base times by height. So what we have over here is 1/2 times by the base, which is 3, times by the height, which is 30. That's the area of the triangle. The area of the trapezium, we have 1/2 times by the sum of the parallel sides. So here we have 30 plus 6, multiplied by the height, which is 2. And then the area of the rectangle, the base of that rectangle, that's t minus 5. The height of that rectangle is 6. And the total area under the curve is equal to the distance. So therefore here we have 550. So with that being said, we can now solve for t. Now, 1/2 times by 3 times by 30, you'd find this value to be 45. So let's just write this here. A half times by 36 times by 2, that's just 36. And here, if we expand out, we have 6t minus 30. And all this is equal to 550. So here we have 6 plus 45, which is, sorry, what was I doing? Yeah, 51. And if we subtract 51 from 550, we get 499. So 60 is equal to 499, and therefore the value of t is equal to 499 over 6. So therefore the value of t, which is what we're finding, if we do 499 divided by 6, that would be 83.2. So we have 83.2 meters per second. Okay, and to the nearest whole number, t is equal to 30 meters per second. For part D, in this question for part D, in a refinement of the model of the motion of the parachutist, the effect of air resistance is included before her parachute opens, and this refined model is now used to find a new value of t. We have to, in this question, see how the new value of t compares with the old value found using the initial, we have to compare with this new assumption how the value of t changes. And we have the following reason. So we can see over here that air resistance would slow the parachutist down, and therefore because it's taking longer for him to come down because he's basically got air resistance slowing him down, the value of t will be greater. Now finally for part E, we have to suggest one further refinement to the model apart from air resistance to make the model more realistic. That's quite easy. We would simply use a more accurate value of gravity. For example, instead of using g equals 10 meters per second squared, we can use g equals 9.8 meters per second squared. For question 2, a small ball P of mass 0.80 kilograms is held at rest on a smooth horizontal table and is attached to one end of a thin rope. The rope passes over a pulley that is fixed at the edge of the table. The other end of the rope is attached to another small ball Q of mass 0.6 kilograms that hangs freely below the pulley. Ball P is released from rest with the rope taut, with P at a distance of 1.5 meters from the pulley and with Q at a height of 0.4 meters above the horizontal floor, as shown in figure 1. Ball Q descends, hits the floor and does not rebound. The balls are modelled as particles, the rope as a light and inextensible string, and the pulley as small and smooth. Using the model for part A, we have to show that the acceleration of Q as it falls is 4.2 meters per second squared. Now, I'm going to begin it with this question by drawing a free body diagram. If we consider the motion of Q, we've got over here, what's pulling us down is the weight, and we have therefore over here 0.6 g, which is the weight, and opposing that we've got the tension in the rope. So that's for the motion of Q. And if we consider the motion of P, the table is smooth, so there's no friction, and the tension is moving the particle P forward. So we have T over here. And we can find the acceleration by simply using F equals ma. So if we use F equals ma, So using F equals ma, if we consider the motion of Q, which we'll do in red, considering the motion of Q, what we have over here in terms of our resultant force, we've got the weight acting down and the tension opposing it. So the resultant force is 0.6 g minus t, and this is equal to the mass 0.6 multiplied by the acceleration a. And now if we consider the motion of p, if we consider p, we've got over here the tension pulling us forward, that's our only force, and that's equal to the mass 0.8 multiplied by the acceleration. So we have over here for p, t equals 0.8a. Now if we add the equations together, we can then eliminate t and from that find the acceleration. So if I call this equation 1 and this equation 2, and if I add these equations together, so if I add 1 to equation 2, on the left hand side we have 0.6 g minus t plus t, that's 0t, and on the other side 0.6a plus 0.8a, that's 1.4a, from which we see a is equal to 0.6 g over 1.4. So if we work this value out, we have 0.6 times by 9.8, and then we divide this value by 1.4, we get a value of 21 over 5, which is 4.2. So we have 4.2 meters per second squared. Now for part B, we have to find the time taken by P to hit the pulley from the instant when P is released. So let's actually think about what's going on. We've got over here Q which hits the ground, and as Q travels 0.4 meters to hit the ground, P will also move 0.4 meters. And as Q hits the ground, the particle P is still moving towards the pulley. Now, we can first of all find the time it takes for Q to hit the ground, or in a similar sense, the particle P to move 0.4 meters, and then we can find out the remaining time for the particle P to get to the pulley. So if I draw out the new motion of Q and P, we have over here the new position of the Q, we'll call it Q dash, and here we've got the new motion of P, we'll call this P dash, and the distance over here that's moved is 0.4 meters, and the remaining distance from here to here is 1.5, take away the 0.4, which is 1.1. So here we have 1.1 meters. Okay, so hopefully that makes sense. So we can first of all find out the time it takes for P to move this 0.4 meters, and then the time for P to move this 1.1 meters. So let's just put all that into words. So after Q hits the floor, P is still moving 1.1 meters to touch the pulley, so we discussed that before, and the time for P to move this 0.4 meters, i.e. the time it takes for Q to hit the ground, we can find. And if we go to the formula book, we can find that time using the formula S equals U plus A plus a half AT squared. So we can find out that time. If we let that time equal t1, then the value of t1 we can find using s equals ut plus a half at squared. We have 0.4, which is the distance moved, equals the initial velocity 0 multiplied by this time t1 plus a half at squared. Remember a from the previous part of the question, that was 4.2, and then we multiply this by t1 squared. So we have 0.4 equals 2.1 t1 squared. t1 therefore will equal 0.4 over 2.1 square rooted. So therefore the time it takes to move 0.4 meters, if we grab our calculator, we have the square root of 0.4 over 2.1. So we get a value of 2 root 21 over 21. Okay. Now, with that being said, we now have to find the time it takes for P to move 1.1 meters to hit the pulley. Okay. So we now have to find this time it takes P to move this 1.1 meters to hit the pulley, and if we call that time T2, we can find out the speed it's traveling at and then use speed equals distance over time to find the time T2. So the speed of P as it moves this 0.4 meters we can find using V equals U plus AT. So we have that speed V, which is equal to U, which is 0, plus AT, so we have 4.2 multiplied by the time it takes to move that 0.4 meters, so we have 2 root 21 over 21. And if we work this out, so if we multiply this value by 4.2, we get 2 root 21 over 5. So we have 2 times by the square root of 21 over 5 seconds. Okay? Sorry, meters per second. Okay? Now, we can therefore say that this time t2, now time is equal to the distance of the speed. So the time is equal to the distance of the speed. Okay, so we have the distance 1.1, and then the speed of this we have 2 root 21 over 5. So working this out, we have 1.1 divided by this, which is 11 root 21 over 84. So we have 11 root 21 over 84 seconds. And therefore, we can conclude over here that the total time is equal to T1 plus T2. So we have T1, which is equal to 2 root 21 over 5. Sorry, 2 root 21 over 21. And T2, which is equal to 11 root 21 over 84. And if we add these together, we come out with 19 root 21 over 84. Okay, so if I add over here, well, if I work this out, 19 divided by 84, and then we multiply this by root 21, something's gone wrong here. 19 divided by 84 multiplied by root 21. That's better. We get 1.04. So we have 1.04 seconds. Okay. And for part C of the question, we have to state a limitation of the model that will affect the accuracy to our answer in part A. Well, one of the assumptions we made is that the rope is light, so that would be a limitation. So for part C, we can say that the rope is light. Okay. For question 3, we have a particle P which moves along a straight line such that at time t seconds, where t is greater or equal to 0, the velocity of P, v meters per second, is modelled as v equals 12 plus 40 minus t squared. For part A, we have to find the magnitude of the acceleration of P when P is at instantaneous rest. Well, it's at instantaneous rest when v is equal to 0. So, with that being said, we've got over here for part A, v, which is equal to minus t squared plus 40 plus 12, and we can factorize this as the product of two linear brackets. We have 6 minus t multiplied by t plus 2. And using this condition of v equals 0, we have 6 minus t lots of t plus 2 equals 0, from which we can see the values of t are either equal to 6 or minus 2. And we know from the question t is greater or equal to 0. So, since t is greater or equal to 0, we can therefore conclude t is equal to 6 seconds. Now, we have to, in this question, find the acceleration, and we can relate the velocity to the acceleration by taking the derivative of the velocity with respect to time. So the acceleration is equal to dv over dt. So we have to differentiate this 12 plus 40 minus t squared. Differentiating 12 we get 0, differentiating 40 we get 4, and differentiating minus t squared we have minus 2t. So the value of the acceleration at 6 seconds would equal 4 minus 2 lots of 6, which is minus 8. And therefore, the magnitude of the acceleration would be 8 meters per second squared. And now for part B, we have to find the distance travelled by P in the interval 0 to 3 seconds. Well, we can relate the distance to the velocity by integrating the velocity. And happily for us, we've been given limits of our integral. That would be 0 to 3, because we're finding the distance travelled in that time period. So, the distance, we'll call it s. That's equal to the integral of the velocity with respect to time. So, s, the distance, is equal to the integral in between 0 and 3 of 12 plus 40 minus t squared with respect to time. So if we integrate 12, we have 12t. If we integrate 40, add 1 to the power divided by the new power, we have 2t squared. And integrating minus t cubed, add 1 to the power divided by the new power, we have minus a third t cubed. And we want to evaluate this between the limits 0 and 3. So, if we substitute in for our limits, we have 12 lots of 3 plus 2 lots of 3 squared minus 1 lots of 3 cubed. And then we subtract off 12 lots of 0 plus 2 lots of 0 squared minus a third lots of 0 cubed. Okay, so S will equal 12 times by 3, that's 36. 2 times by 3 squared, that's 18. Minus a third lots of 27, that would be minus 9. So therefore the distance travelled in that period would be 45 meters. So that concludes the end of the paper. Don't forget to like, share and subscribe. Any questions, please feel free to comment them in the comment section below. I hope you enjoyed this video. Thanks for watching.